Hello. This is going to be a big video, and it's going to be on the first really important and powerful fact in group theory. But first, I will have to talk about some technical construction of cosets, and using them, using their properties, we will be able to quickly deduce what is called Lagrange's theorem. Which can be packaged easily in a nice numerical form, giving us some restrictions on the sizes of groups and their subgroups. And although it might sound innocent, it's really a powerful result. So let's start with this coset construction. The input for this construction is a pair of a subgroup sitting inside a group. So I have a subgroup in my group G. What I'm going to do with it, I'm going to break G into the disjoint union of equivalence classes, and it will be done using a certain equivalence relation. So I will introduce an equivalence relation, coset relation, which will be really using this data of a subgroup. So I'll say that two elements in the group, F and G are arbitrary elements in my group, they are equivalent if there is something in the subgroup which I can multiply the first with from the right and get the second. So that is the definition. Please check this fact that is an equivalence relation. And as any equivalence relation, it will break the whole set, G, into a union of, disjoint equivalence classes. For this equivalence relation, equivalence classes are called cosets. Well, we're using the right multiplication, so they're right cosets. With respect to the subgroup H. So if we want to see just one equivalence class, we will pick up an element as usual with equivalence classes. So start with an element F and look at everything which is equivalent to it. So we will look at all G's which are equivalent to F. And G's which are equivalent to F are products of F with something from H. So I can write it compactly like that. Capital H allows me to take anything from here and multiply with a fixed F, get a product computed in the group, and that is in my coset. So this is the compact description of my coset of F. So here is an easy but important fact. I'll call it lemma. That the number of elements in all these equivalent classes, in all these cosets, is the same. If it is the same as the coset size of the coset of the identity element of my group, a special element in my group after all, but that coset is just the subgroup itself. And here's a proof. Well, to see that the number of elements in two sets, the numbers are the same, I have to set up a bijection between them, and here's my bijection. So going from H to the coset of F, I need to devise a bijective, or rather even better invertible map. And here's it. So I take H and I multiply it, of course, with F, multiplying from the right. That puts me in here, and I see all the elements in here once, so that's a bijective map. Yeah, I have the inverse map, which will just divide by F an element from here, so strip this F from, and the product and get the answer in each. But anyway, this is a bijection, and so the numbers of elements will have to be the same. Done. So now we are ready to prove this Lagrange's theorem, which really says that the number of elements in a subgroup will have to divide the number of elements in a group. The order of a subgroup divides the order of the group. So maybe just call it theorem and put Lagrange in brackets. And I will write it in a numerical formalic way. So the order is of the group, of the larger group, is the product of the order of any of its subgroups and something else. What is this something else? It's called the index, and this index I will define here as the number of cosets. So let me introduce first the set of cosets. Write each coset. So I'm looking at subsets of my group G, which are these equivalence classes. One of them is H itself, others are represented by some other elements, but I have a finite number of them. Is my group is finite, and that's what I count here. This is the size, this is a number of equivalence classes, this is a number of cosets, and that's what I have here. So that is the ingredient in this division statement. The division statement says that this number divides that number, but really it's writing the larger number as a product. So here's a proof. Again, it's going to be very short. So G is a disjoint union of cosets. Just by counting elements and distributing them among cosets, each coset will have that many elements, and that is the number of those cosets, and we are done. Again, very short. So now let's collect benefits. So the first consequence are going to be the following. Let's take an arbitrary element in the group. So we had this cycling behavior of this element controlled by the order. That is this smallest power of this element, which is equal to the identity. Then we can be sure that this is a divisor of the order of the group. Must be. Well, how can we extract it from Lagrange's theorem? So let's remember that the order is the number of all, also the number of all different powers of G, and as such it is the order of the subgroup, cyclic subgroup of G. But by Lagrange we know that this being a subgroup, the order of it has to be a divisor of G, and so we're done. We're done again. So that is what we can use, say, proving Euler's theorem, and Fermat as well, but Euler's is really a place where we benefit from this group theory. Let me finish with last consequence of that, saying something very specific about all groups of a given order. But yeah, I assume that this order is a prime. So I'm going to conclude that any such group has to be indistinguishable isomorphic to the group of integers modulo that prime. So there is only one and only group of a prime order. Well, let's recycle the previous result. Let's take an element in our mysterious group Let's take it such that this is not the identity element, because if it's identity element we cannot go far. But if it's a non-trivial element, and it should be if p is bigger than 1, if p is 1 we don't have anything to do, but if p is bigger than 1 we should have such elements, and that's just form its cyclic subgroup, or whatever compute the order of it. So the order of it, or the order of its cyclic subgroup, should be bigger than 1, because we have in it we have identity and we have G and they're different. But it's at the same time has to be divisor of the order of the group, which is the prime. And with this squeeze there is no other alternative but for this to be of order P. So among the powers, that's what this cyclic subgroup is. Among the powers of G we have P different answers. And we only have P different elements in the group. So the whole group consists of powers of G. But powers of G as a group operate exactly as integers mod the order. And so we are done. Now that is the first really classification result, just looking at the size of the group and the order, giving all possible answers. We'll try to reach more, but that is really the first and probably the most widely used. See you later. Bye.